Hello everyone and welcome to MV Tutors. I'm Solo and I'll be starting off the physics paper. So looking at paper 1, question 1. Don't mind me with my cowboy hat. I actually took it from my son. Thought it would look cool. But yeah, let's get right to it. 1.1. Consider the statement below. The perpendicular force exerted by a surface on an object in contact with the surface. Okay, which one of the following forces is defined by the statement above? Okay, so when I think perpendicular, remember if you have a surface here which is perpendicular and you have whatever object you have, you know that the force acting on this object from the wall or the ground or whatever, it's going to be in that direction, right? Which would normally be your normal force. Okay, so yeah, so in this case we're going to look for the term normal force. So it doesn't matter in which direction. It could be something, I'm failing to do a straight line, but it could be a box on a surface. No matter in which way that surface is put, it could be just flat, it could be the ceiling and you're pushing something against that surface, but basically from the surface to the object, that would be your normal force. Okay, so let's see, do they have normal force there as an answer? Yes, they do. So 1.1 would be A. Resultant force, no. Frictional force, no, not necessarily. Gravitational force, no. So the one that's applicable here really would be the normal force. Okay, and then 1.2, two balls of masses m and 2m are dropped simultaneously from the same height above the ground. Okay, so what are they saying about it? When the balls strike the ground, which one of the following physical quantities will be the same for both balls? Okay, so if we look at the weight, you know that weight is equal to mass times gravitational acceleration. So G would be the same, but because they have different masses, that won't actually work. Okay, if we have a look at velocity, okay, so velocity doesn't really depend on their weight. Okay, velocity, remember, that is just distance divided by time. Okay, maybe I should write out distance so that you don't wonder what that D is. So velocity could be distance covered or average distance over time. Okay, so if they are being dropped from the same what is it? From the same height above the ground. Okay, so they have the same distance. Okay, another thing is that they travel at the same time. If you drop two objects from the same height, okay, without considering air resistance, would they reach the ground at the same time? Yeah, they would. They would. So far, velocity seems to be winning. Okay, but let's have a look at momentum. Okay, so if we have momentum over here, P is equal to mv. Again, the mass is different, so their momentums will definitely be different. All right, if you look at kinetic energy, okay, I'm just going to use ek. Some of you use ke. Okay, I'm used to ek. So that again, half mv squared. This mass over here will ruin things. So the right answer we would go for in this case would be B. Okay, so this is our answer, B, and then that was A. Okay, so yeah, we are done with 1.2, and then let me just zoom in here a little bit. Okay, 1.3. So it says the graph below shows how the momentum of an object changes with time. Okay, if you're going to have momentum changing with time, we're looking here at impulse. Okay, so now it says during which one of the following time intervals measured in seconds is the magnitude of the net force act on the object the greatest? Okay, so let me just bring this a little bit up so that we can answer there 1.3. Okay, so if you look at your formula sheet, there is an equation there that talks about the net force, okay, and that net force being impulse, because change in momentum is impulse, so it'll be impulse over the change in time, okay. And if you have really a look at this equation, I don't know if you can see that it's like getting the gradient. Remember gradient, change in y over change in x. So if you have a look here, change in p, that is like on your y-axis, and change in t, that's on your x-axis. So you know, the sort of like link. So you could say the net force, if you want to know, looking at the graph, where is the net force the greatest, it is where you have your steepest slope, okay. Because if you just think about it as well, when you have a very steep slope, your gradient is quite high. If you have a very small slope, your values are quite low, okay. So let me just remove that. That was just somehow where you relate your maths into your physics, okay. So let's see, if you go from 0 to 1, ne? I mean, you could even calculate this if it's really difficult for you to see. So if you go from 0 to 1, let's say we were calculating it, ne? For the option of, let's say, A, B, C, and D, and then we'll see what actually happens, okay. Maybe let me not put those dotted lines. So what would be the gradient at A? So A, you go from 0 to 1, ne? So your change in time, that's just 1 second. And then your change in, momentum, which is impulse. So you go from 20 to 0, okay? So basically you have 20 there over 1, okay? Now we have a look at B, which is from 1 to 2 seconds. So again, you still have 1 second, the change in time, and then the change in momentum, well, you have, it goes from 20 to 10. So that's basically minus 10, because you take your final minus initial, okay. If we look at C, which is 2 to 3 seconds, again, that is, change in time is going to be 1, but we are going from so we're going from 10 to minus 10. So you have minus 10, that's minus 20, okay. And then lastly, from 3 to 4 seconds, again, the change in time is just 1 second. And if you take your initial, which is minus 10, final, which is 20, so 20 minus 10, that will be 20 plus 10, that's 30. So we can see here, like they're saying, during which one of the following time intervals measured in seconds is the magnitude of the net force acting on the object the greatest? That would be D, okay, because we can see here you're going to get 30 for D, okay, 30 newtons to be exact. So D is the winner in this case, okay. And then we go to 1.4. All right, let me just shift it up a bit. Okay, it says a ball is dropped from a height above a floor, okay. The ball makes an elastic collision with the floor at time t0 and bounces vertically upwards, okay. So elastic collision, what do you remember about elastic collision? Well, basically we're saying that the sum of the kinetic energy before is equal to the sum of the kinetic energy after, okay. Initially, initial and final. So I used before, maybe I should just use initial, okay. So initial is equal to the sum of the kinetic energies after, okay, or final. So now it says, which one of the following graphs shows how the total mechanical energy of the ball changes with time? Okay, guys, so first of all, it was dropped, okay. If it were dropped, let's say a height above the floor, so there the ball was before it was dropped. So it had potential energy, but it did not have kinetic energy because it's not in motion yet. Okay, and then they drop it, right? So as it drops, remember, if you're dropping something or if something is being thrown, as it goes lower and lower, the velocity keeps increasing. Okay, so at the bottom there, when it reaches the floor, so let's say this is the floor. So by the time it reaches the floor, it would have its maximum kinetic energy, but there won't be any potential energy at that point because it has reached the floor. Your height would be 0. So here, potential energy decreases, okay? Whereas your kinetic, okay, maybe not put it that way. So as the ball falls, the potential energy decreases, but your kinetic energy increases because the velocity is increasing. Okay. But your mechanical energy, guys, what is mechanical energy? Okay, so so mechanical energy, well, basically that would be the sum of, or the change in kinetic energy plus, the change in potential energy. Okay, and anywhere where you get, if you take any section, okay, you actually find that your mechanical energy stays the same. I don't know if you got me. So if you take your potential energy here at the beginning, that'll be your maximum. Your kinetic energy will be minimum, or it'll be 0. Okay, so you'll have a value. Let's say the potential energy is 5 joules. Okay, now when you get to this point over here, your potential energy would have reduced, and by the change in that reduction, that is actually equal to the kinetic energy at that point in time. So you will still have 5 joules at this point here. Even when you get here, your kinetic energy is really increasing, your potential energy is really decreasing, you will still have 5 joules. That is the mechanical energy that I'm talking about here. It is always going to be constant. When you get to the ground, your kinetic energy would have been its maximum, which is 5 joules, and your potential energy would be 0. So again, we would have 5 joules. So in this case, if they only spoke of kinetic energy, yes, it would be different. If they only spoke of potential energy, it would be different. But we are speaking about the total mechanical energy. I should have actually put mech total over there. The total mechanical energy will stay constant. Okay, I really hope you got it. So in this case, if you look at the graphs there, it would be B. I'm just looking for space. Let's just take it a bit up. So just looking at the graphs, I won't even bother investigating others. I'm just looking for the one that's just constant because the total mechanical energy is constant. Okay, so we would go for B. Now we go to question 1.5. Okay, let us just zoom in. Okay, let's take that a bit up. Okay, so consider the 2 spectrum diagrams below. We have diagram 1 and we have diagram 2. So diagram 1 represents the spectrum of an element in a lab on Earth. So that's basically like your reference point, okay? And then diagram 2 represents the spectrum of the same element from a distant star as observed from Earth. Okay, so because it is the same element, you are expecting, like for example here, if you look between these 2 lines, the distance between them should be the same even for diagram 2. Okay, it's just that as you see with diagram 2, there has been a shift. Okay, and I hope as I'm talking about a shift, what's coming in your mind is the red shift, the blue shift. I hope it's starting to ring a bell. Anyway, so it's saying, which one of the following can be deduced from the spectra above? 1 spectrum, 2 spectra. Okay, English. So let me just take it up a bit there. Okay, so now we know that, okay, let's just have this. You have a blue shift, you have a red shift. Okay, we know that blue Blue actually has a higher frequency. If you're going to look at your spectrum, your colors, especially, you start with red, then you go to orange, yellow, green, blue, violet, roig, biv. Yeah, that one. So when you get to blue on the other side, or violet, it normally has a higher frequency, but a shorter wavelength. Okay. And when you get to red, it actually has the lowest frequency, but the highest wavelength. Okay. And that can actually be used to explain why the sky is blue during the day, and then during dawn and sunset, it's actually like reddish, orangish, yellowish. That's where it comes from, but that's another story for another day. Okay, so now when you get to have a look here, so once you have your reference, okay, so diagram 1 is your reference, okay, what happens on Earth, you need to have a look now. I don't like it when I don't have straight lines. Let's rather do a wavy line. So when you have a look at your reference, you must decide, where did this thing shift? Did it shift to the right, or did it shift to the left? Okay, so if it shifted to the right, then you're going to look at the red shift. Okay, and if it shifted to the left, then that would be your blue shift. Okay, so anyway, I didn't even read the options. So now it's saying, which one of the following can be deduced from the spectra above? Okay, so the star is moving towards the Earth. Okay, the star is at rest relative to the Earth. Okay, if it were at rest relative to the Earth, then you wouldn't have any shift. Okay, the star is moving away from the Earth. All right, both the star and the Earth are moving towards each other. Okay, fine. If it's moving towards the Earth, guys, it means that your wavelength is actually shorter, ne? And your frequency is high. Okay, so we'll be looking at a blue shift, more or less. If it is moving away from the Earth, it means your wavelength is longer and your frequency is shorter, so we'll be looking at the red shift. Okay, but looking at our diagrams, the second diagram actually is shifted to the right, which is the red shift. And if it's the red shift, it means it's moving away because the wavelength is longer. Okay, so we are gonna go with C in this case. Okay, and I hope that was clear. All right, so yeah, now we get to 1.6. Let us again move it there. Okay, this diagram, I don't know what you see when you look at this diagram, but I used to, the way our teacher drew it back in the days, it looked like a girl with like ponytails and hair just going out, but now it looks like eyes and the tears are going in every direction. But anyway, it says the diagram below shows that the field lines for the combined electric effect due to two small charged spheres, P and Q. Okay, so we see P and then we see Q. So what does that tell you? You see, when we have P, your electric field lines are actually moving away from P. Okay, so if they're moving away from P, then we know that P is actually positive. Okay, and then when it comes to Q, okay, so this is P and that's Q. When it comes to Q, they're actually moving inwards. They're going towards Q. And that's how I know that we actually have a negative there. Okay, so your electric field lines actually, they're actually moving, in this direction from positive to negative, basically. Okay, yeah, and yeah. So what is happening? Which one of the combinations below correctly shows the polarity of spheres P and Q? So we know P has to be positive, so we're looking at the options C and D. And then Q is negative, so our answer is going to be D, okay, because both of them can't be positive, okay, or else they'll repel each other. Okay, so our answer for 1.6 is D. Okay, 1.7. Alrighty. Just trying to make sure. Geez, I hope I haven't been hiding the question in my face. Maybe let me get it a little bit smaller. Okay. But it says two identical spheres. Just right there. Okay. So two identical spheres, P and Q, carry charges positive Q and negative 2Q respectively. So they're identical probably in size and everything else, but they are carrying different charges. One is positive, one is negative, and the other is actually twice. Okay, so negative 2Q and positive Q. Now, sphere P exerts an electrostatic force of magnitude F on sphere Q. Okay, if you remember the equation, the force applied, well, you have your constant, and then there's Q1, Q2, and you have R squared. Okay, yeah, which one of the following represents the magnitude of the electrostatic force on sphere Q on sphere P by sphere Q? Okay, so if you're going to calculate the force on it, guys, both P and Q are actually gonna apply the same force to one another. Okay, just because P has positive Q and Q has negative 2Q doesn't mean the force now is gonna be half or 2F or 4F or whatever, but they're actually gonna apply the same force to each other. Okay, so if you're gonna say I want the force on P by Q, okay, you are gonna then substitute. Okay, fine. So for P I have Q, and then for Q I have 2Q, and then there's the same distance. Now if I wanted to get force on Q due to P, same thing. So I would have K, and then I would have 2Q, K, and I would have Q and R squared. So basically they just really applying the same force to one another. The other won't be half or twice or even 4 times that. If the distance between them started changing, okay, then yeah, you know, things would be different. So in this case, our answer would be B. Okay, so 1.7 is B. And now we move to 1.8. Let me just shift. We're almost there, guys. We're almost there. Thank you for bearing with me. Okay, 1.8. Now let us see. So let me just zoom in a little bit. In the diagram, the circuit diagram shown below, all the resistors are identical. Okay, at least that's nice. You don't have to now factor things if they're not identical. So it says ignore the internal resistance of the cell. Now the question, which voltmeter will have the highest reading when switch S is closed? Okay, so remember, if switch S is open, the only reading you're going to have in the circuit would be V1, and V1 will be equal to the EMF. Okay, because there's no current flowing. So if there's not current flowing, you have a reading on V1, you have a reading on V2, on V3, and V4. I actually want to make some marks. Okay, so now they're saying which voltmeter will have the highest reading. So let's say now we have closed the circuit. Okay, it's closed, and now we have current that's flowing. So it flows from the positive to the negative. So you have this current. Let's say hypothetically, let me actually use a smaller yeah, so you have current flowing. Maybe let me just go back there. So if you have this current flowing, because the switch is now closed, let's say your current is like what, 2 amperes. Ish, can I go back? No. So let's say it's 2 amperes. If it's passing through where V1 is, if it's passing through resistor, that resistor here, it'll be the full 2 amperes passing, right? Okay, then it goes all the way, it goes all the way. Now it gets here at this intersection. Okay, portions of that current will go here. Okay, another portion will go here. All right, so already this current is low. And if the current is low, it means your voltmeter reading will be low. Okay, and then it comes here, guys. There's another intersection. So that portion here has to be divided again and divided here. So already, so for V2 and V3, it's out. It's not going to be its maximum. Okay, so remember also for V4, it's the shared current. Where the current flows fully through, it's actually where voltmeter 1 is. And you're going to have the highest reading when switch S is closed at V1, and V1 is A over here. Okay, I hope that was understood. As soon as you start dividing the current, okay, then you won't have the highest voltmeter reading there. Okay, cool. Now let us go to question 1.9. I hope you can see it properly on your side. Sorry if I'm hiding it. In which one of the following electrical machines is electrical energy converted to mechanical energy? Okay, so with this, when you have a generator, okay, this is the simplest one to remember, because with a generator, we all want electricity, right? And we would know that in South Africa because of load shedding. So for a generator, you have mechanical energy being converted to electrical energy. Okay, with a motor, you basically have electrical energy being converted to mechanical energy. Okay, so now it says, in which one of the following electrical machines is electrical energy converted to mechanical energy? So as I'm looking for the answer, I want to see a motor somewhere in my answer. Okay, and that I see generator for A, B, so no. C, AC dynamo. In that exam, I'm like, what in the world is a dynamo? And then D, DC motor. So yes, I would definitely go for D. Okay, because that is my DC motor. Well, whether it was the AC or DC motor, it's a motor. That's pretty much it. And then we are at the end, guys. 1.10. Okay. So 1.10. Okay, so 1.10. Which one of the following combinations correctly links an emission spectrum and an absorption spectrum to the energy transition of an electron in an atom? Okay, so I decided to just pause a bit, write down the little bit of theory. I didn't want to take much time. And then we'll choose which one is the correct. So what happens during emission spectrum? Well, basically the gas is heated first of all, and then the electrons absorb that energy. And when they do so, they go from the ground state and they start moving to higher energy levels. Okay, and then at some point, you know, it's not like a permanent thing that they end up at that high energy level. They will go down eventually. Okay, and when they fall back to the ground state, photons are given off. So if you shine a light on that whole scenario through like a prism, a glass prism, you will then start seeing the emission spectrum. Okay, so we know with the emission spectrum, the electrons will move from a high energy to a lower energy level. So if we look at our options there, basically we are, you know, left with C and D. So what happens on the absorption spectrum? Okay, let me just show it there. So basically light is passed through a cold gas. Okay, and now the energy of that light that passes through the cold gas is absorbed by electrons in that gas. Okay, and basically what would then happen is the absorption spectrum forms as the electrons, obviously they will get that energy. Okay, the electrons will get the energy from that light, you know, and move up to a high energy level, but the absorption spectrum itself will only be seen once they drop from a high energy level to a lower energy level. So with the emission spectrum, the that emission spectrum is seen when the electrons go from a high to a low energy level. But with the absorption spectrum, it's actually when the electrons have absorbed that energy from that cold gas, or the light that passes through the cold gas. So when as it goes from a high to it goes from a low to a high energy level, then it would emit the absorption spectrum. I hope I didn't confuse. Sometimes in your mind you're saying something but the words are different. So emission spectrum, it is shown when the electrons, after absorbing that energy, go from a high energy level to a low energy level. With the absorption spectrum, the electrons, as they go from a low energy level to a high energy level, that's where you see the absorption spectrum. I hope it makes sense. So on the absorption spectrum side, remember we only have two options here, C or D. So for emission spectrum, we said it goes from high to low. Okay. For the absorption spectrum, it has to go from low to high. And in that case, that would be D. Okay, so our answer for 1.10 is D. And we are done. I will see you guys next for question 3.
Well, good day to you. Welcome to MV Tutors. My name is Figa and I will be your tutor today. We are doing the November 2021 Physical Science Paper 1, and I'll be doing question number 2 with you. Okay, let's get right into it and waste no time. Okay, so it says a 20 kg block is placed on a rough surface inclined at 30 degrees, as you can see there, to the horizontal. A constant force F acting parallel to the surface, force F acting parallel, is applied on the block so that the block moves up the incline at a constant velocity. Okay, so if something is in constant velocity, that means acceleration is 0, okay, of 2 meters per second. Refer to the diagram below. A constant kinetic frictional force of 18 acts on the block. Okay, so we see it over there. Now the first question says, state Newton's first law in words. Okay, so Newton's first law is basically saying that if you have an object, it could be a block such as this, an object that is at rest or moving at constant velocity, it will remain at rest or remain constant unless acted upon by an external force. That's just it. Okay, so question 2.2 says, draw a label free body diagram for the block. Okay, so that block there, I'm just gonna say 2.2 over here. So that block here is represented by that. So first of all, what we can notice is that there's a force F moving that way, like that. Okay, this is a force F. And then what else do we know? We know there's a weight going right straight down. Okay, so I'll call it W. Okay, because weight, remember, weight is mass times gravity. And then opposite the force, we're obviously gonna have a friction force moving the opposite direction. I'll call it FF. That's the frictional force. Okay, so that's it. But additionally, what I just want to add here is that you can resolve this W so that it's in the same plane as these. Okay, and in resolving it, it's like that. Okay, your 30 degrees will be over there. It's gonna be 30, and then this it's gonna be W. This is adjacent, so it's cos theta, or cos 30, and then this one going that way is actually coming from here to complete the triangle like that. Just move it up there and then it becomes W sine theta. Theta is over there. Okay, so be cognizant of that. So there's two ways you can draw this. You can include these and remove that, or just put that. Okay, so one more thing, you got a normal force going that way. Okay, so that's one plane and that's another plane. Cool. Next question. Calculate the magnitude of the force F. Okay, so now if we look at the force F, this is now 2.3. If we look at the force F, we've got that. Okay, we're gonna make it positive going to the right. So we got a positive F and then a negative frictional force that's going the opposite direction. And also another thing going the opposite direction is that W sine theta, right? And all of this is going to be equals to mass times acceleration. What does this come from? It comes from F net is equals to mass times acceleration. So the net forces, these are the net forces acting on the plank. Okay, so we can start filling these in. F stays F minus frictional force we have been given is actually 18. There it is. Minus W, remember, is mass times gravity. So let's go check, are we given the mass of the block? Okay, 20 kg, so we've got 20 times 9.8. that just represents the W, and then we can put then sine theta is 30. This is equals to mass, which is the 20, times acceleration. Remember, this thing is at constant velocity, so constant velocity means acceleration is 0. Okay, now we should put everything in a calculator. All right, let me bring up a calculator so that we can do this real quick. So if I take everything to the other side, I'm gonna have 18 plus 20 times 9.8 times sine of 30, close that bracket, it's equals to 116. So F is equals to 116 and it's in newtons. That's it, just like that. Okay, right. Okay, let's move on to the next question. Let's put that down. It says 2.3, we just solved it, so we're on 2.4 now. Okay, let's just read it before. So force F is removed when the block reaches point X on the surface. So where's point X? There it is. So it's like the force is pulling, and then when it reaches here, they release the force. Then what happens? the block continues to move up the surface and comes to rest momentarily at point 1. So of course, moving the force, it can move a little bit and then it stops eventually. So when the force was there, it was constant velocity, and then once you remove the force, this thing started decelerating, meaning slowing down. Okay, and then what? Assume the kinetic frictional force acting on the block remains at 18, okay, as it moves from x to y. All right, write down the net force acting on the block as it moves from x to y. Okay, let's do this. This is now 2.4. So like I said, from x to y it starts decelerating. Okay, so what does that mean? It means, okay, it was accelerating with the force. I mean, it was being moving up with the force of 116, and then once you remove it, it decelerates. But they want the net force. Okay, so the net force then is going to move opposite, okay, and opposite this force. And because you've removed it, what you're left with is still 116, but it's going on the negative side. Okay, so your F net is still 116. It's just that it's going on the opposite direction now. Because look what happens. All you have done is that you have just taken away the force, and then you're left with friction and this W sine theta. That's what you're left with. So if you add these up, you still get 116. Only difference is now it's on the negative, meaning it's moving backwards. Okay, or you can say it's 116 newtons but moving backwards. That's what the negative means. It's moving backwards. Okay, and then they say calculate the distance between points x and y. Okay, distance between x and y, we can do that. All right, so let's get more space. Cool. So this is now 2.5. Distance between, we need an equation of motion. The one I can use is Vf squared is equals to Vi squared plus 2a change in x. Okay, and what do we want? We want the change in x. What do we know? We know that our final velocity, because it comes to rest, is 0. So that's 0 squared. Our initial velocity as given in the question they gave us there is 2. Constant velocity of 2. Remember, at x is at 2, and then they let go. By the time it reaches y, the velocity is 0. So here we'll have 2 squared plus 2. Acceleration, we don't know acceleration. We need to calculate acceleration. Remember, it is actually decelerating. Okay, fortunately we can calculate acceleration on the side. We can say okay, we know F net is equals to mass times acceleration. So we know our F net is actually because it's decelerating, is minus 116 is equals to the mass of 20, and a, what's the deceleration? can solve it. It's just gonna be 116. Let's bring our calculator back. Minus 116. Why did I say minus? Okay, let's just do it. Divided by 20. Let's change it to decimal. That's a negative 5.8. Okay, so then we can come back then to our equation here and put negative 5.8. You have to put negative because it's the directions. If you don't put it in, your answer is gonna be wrong. Okay, and then change in x. Now we just need to do some mathematical gymnastics. Therefore, change in x is gonna be 2 squared. If I take this 2 squared to the other side, becomes negative 2 squared, and then I need to divide it by open the brackets, 2 times 5.8. Cool. And my final answer is 0.34. Okay, I'll leave it in 2 decimals. They didn't say anything about number of decimals, did they? No, nothing. So I'll just leave it at 2 decimals. So that is in meters. That's my final question. Well, that's it for question number 2. I hope you understood, but in the event that you didn't, I'm available to tutor you. Just contact me via my website www.mvtutors.co.za, or you can WhatsApp me on 076 312 1107. Now, before you contact me, please talk to your parent or your guardian and make sure they are involved in the process, because remember, at the end of the day, they are the ones that are gonna be paying for my services. Okay, well, that's it from me. Thank you so much for listening, and I appreciate you.
Hello everyone, and welcome to MV Tutors. I am Tulu, your cowgirl for this paper one. We'll be looking at question 3 now. All right, so let's get to it. It says a hot air balloon is moving upwards at a constant unknown speed. Okay, so it is moving at a constant unknown speed upwards. All right. And the first question basically says, is the hot air balloon in free fall? Okay, yes or no? Well, it ain't falling. That's what I can tell you. Okay, so I would go with no. And give a reason for your answer. Well, first of all, it's moving at a constant. Okay, yeah, let me write proper. Okay, so it is moving at a constant speed. Okay, so we know that if something is moving at a constant speed, constant velocity, it doesn't have acceleration, but gravitational acceleration is still acting on it. All right, but it's not the only thing acting on it. There are other forces that are acting on it. Okay, so with free fall, the only thing acting on the object busy falling is gravitational acceleration. In this case, that's not the case. It is moving at a constant speed. It's not only gravitational acceleration that is acting on it. There are other forces as well. Okay, so because it is moving at a constant speed, what I would also say is, okay, it's moving at a constant speed. That's one thing I would say. The second thing is, I would say that the acceleration, okay, the acceleration, or let me just say A. So if I were to do calculations, acceleration is not only due to the gravitational acceleration. Okay, so yeah, that's where I would leave it. Yeah, that's it. It's not in free fall. The hot air balloon is not in free fall. Okay, now let us see what we have here. Okay, so now it says when the balloon is 200 meters above the ground, a small stone is dropped from the balloon. So if it is dropped, okay, we know that the initial velocity is 0 because it is dropped. All right, but in this scenario, things are a little bit different. Imagine you are in a car or a moving van and you're sitting at the back of the van. Okay, this van is moving at a speed of 80 kilometers per hour. Okay, so if you were to be sitting in that van and you happen to move from one side to the other, okay, what speed are you going at? You will be going at the same speed. Okay, let's say you're sitting still. Let's not complicate the problem. If you're in a moving van at the back and you're just sitting, is your speed the same as that of the van, or is it 0 because you're sitting still? Okay, so if you were to jump, let's say let me just move this upwards. So there you are, we have the van. How is the van going to? Okay, something like that. Ooh. Okay, yeah, drawing it. So we have the van, those are the wheels, and there you are. And this van is moving at 80 kilometers per hour. If you were to decide to jump while this van is moving, are you gonna jump and then the van is gonna leave you behind and you're gonna fall on the road? You're not, because you're also moving at 80 kilometers an hour. And we see that when people don't have their seatbelts on and there's an accident. So if you don't have your seatbelt on, this vehicle is moving at whatever speed, and then you get into an accident, you will say sometimes, like the car will just throw you out. Okay, or maybe you'll hit against the window and not necessarily come out. Okay, so that is why we have to wear seatbelts. So you are moving at the same speed that the vehicle is moving in. Back to the rock. Okay, like I said, if you were dropping it, maybe you are standing on a building and you just happen to drop a stone, for sure the initial velocity would be 0. But because this hot air balloon is moving at a constant velocity, or it's moving, whether it's constant or not, it's moving. The initial velocity of the rock or the stone as it is being dropped, remember, it's moving at this constant speed, okay? And then it's dropped. So it will have like a parabolic, what can I say, motion. If you were to plot the displacement versus time graph. Okay, so what do I mean by parabolic? You're like, what's happening here? Okay, oh snap, things are happening here. What's happening? Okay, all right. Okay, so by parabolic, you would have your hot air balloon there. Okay, yeah, something along those lines. Okay, and it is busy moving up at a constant speed. Okay, so let's say speed is equal to x meters per second. It's moving up, and then because it's moving up with this stone, so both of them are both moving at this constant speed x. So if you're gonna throw, or rather drop the stone, initially it's still going up, and then finally it will. So that's what I meant by parabolic. If you were to draw the displacement time graph, it would move parabolically. Okay. By the way, now if you're inside there, you just see the stone dropping like that. Okay, so yeah, that is the scenario there. All right, so stone A is dropped from the balloon. See the diagram above. And then another small stone B is dropped 5 seconds later from the balloon while the balloon is still moving upwards at a constant velocity. Okay, so we drop stone A, it reaches the ground, and that distance between is like what, 200 meters. Okay, it reaches the ground at whatever time, but it strikes it at 62.68 meters per second. All right, and then later on, while the balloon is somewhere up there, then you throw another small stone B. Okay, let's just remove that ugly picture. And yeah, so let's see what they are asking. Okay, let us go to the other question. All right, so 3.2. Okay, so calculate the speed of the hot air balloon. All right, now you're thinking, what? How? This thing is moving at a constant speed. We don't know, we don't have much regarding this balloon, okay? So how are we going to do it? Well, I would then use the stone, okay? Because we know that the initial velocity of the stone is actually the velocity with which, or rather the speed at the pace that this balloon is moving, this hot air balloon. So the initial velocity of the stone A, it will be the same as the velocity of this hot air balloon, okay, because it's constant, it doesn't change. Okay, so we'd use the stone as a reference. So if you're going to look at the equations of motion from your formula sheet, you would then use this formula here. Okay, so we're just gonna make a note there, okay, that the speed of the balloon, this constant speed, is actually equal to the initial velocity of the stone. And when we look at the stone, now the stone, it is definitely in free fall. Okay, so we can apply the equations of motion here, okay, because we know that G will be 9.8. Okay, it's accelerating downwards. Okay, it's in free fall. So we can then use the equations of motion, and if you choose it there, we have the final velocity, or rather the speed of the stone. We are looking for the initial, which will then give us the speed of the balloon. And oh, one thing I did not discuss is the direction. Which direction am I going to take as positive? I like choosing downwards as positive simply because most people choose upwards as positive, so let's go the other way. Okay, and also because gravity is always acting down, I can use a plus here instead of a minus. Okay, so I can use a plus. All right, so we know that our final velocity is 62.68. That will be squared. We are looking for the initial velocity. Okay, we know that our gravitational acceleration is 9.8, and we know that this distance where the stone was thrown to until it reaches the ground, it's actually 200 meters. Okay, and because the stone is busy going down and we chose down as positive, you will leave this value here as positive. Okay, and then we can solve. All right, so I'm just going to take the initial velocity to the left side. Or you know what, actually, I'm taking, yeah, this is now where you do the maths. I'm going to take this whole term to the left, but I'm going to make the initial velocity the subject of my formula. So then I would have 62.68 squared minus 2 times 9.8 times 200, and let's just take this a little bit up. Okay, and we can then actually get the square root. Okay, so that we don't have to rewrite everything again. And then we will use our calculator. Alrighty, so we have the root of 62.58 68 squared minus 2 times 9,8 times 200. Okay, so we have 2,96 meters per second. So this was the initial velocity of the stone, but actually the speed of the balloon finally it is actually equal to 2,96 meters per second. Okay, I am going to save this answer. I'm going to store it under A. Okay, so if I choose alpha A, 2,96. Okay, yeah, because yeah, you know, as soon as you start using rounded off values, the answer at the end just becomes something else. But they are gracious enough to have a range with which your answers can fall in because they understand. Okay, the markers, that is. All right, just in case you're like, what? Who's they? All right, and then now we're going to go to 3,2,2, 3.2.2. The time it takes for stone A to strike the ground. Okay, so like we said, the motion of this, if you were to plot it on a displacement time graph, it would be like this. So this is where this hot air balloon was, okay, when the stone was thrown. Okay, and now it went up. Obviously this is exaggerated, you won't really see that curve. It's exaggerated. Okay, so there was a point where it went up. Okay, and because my up is negative, because I chose downward as positive, and there's a point where it went down. You can do this in one formula, one calculation. I just like separating it because in my mind it makes sense. I'm seeing it visually, so my calculations have to formulate what I'm seeing in my mind. So the time it takes for the stone to hit the ground, well, first of all, it will go up, right? So there's that initial velocity that we just calculated now, and then it comes to a point where the velocity is 0. So this would be the final velocity for the motion going up. For the motion going down, well, the initial velocity is 0, but the final velocity, it was given to us as 62,68. So that's basically what we will be using going forward. So you're going to look at your equations of motion and see which one should I choose, which one should I go with. Okay, so I have chosen where I have my final velocity, my initial velocity, and I am looking for time. Okay, so we have our final velocity. We set it at 62,68. Our initial velocity, we calculated it, it's 2,96. And okay, let me choose here. This is the upwards motion. Okay, so gravity is always going down. Okay, ooh. This is way now. So the final velocity, remember when it went down? No, what am I doing? I'm looking at the upwards motion. Upwards motion, let me not confuse myself. Okay, so with the upwards motion here, the red one. Okay, so our final velocity, I said it now, I forgot it, it's actually 0. Okay, the initial velocity, because it's going up, it's going to be negative for me because I chose downwards as positive. So initial velocity is negative 2,96, and then gravity is always going down, so that will be positive. And then we're looking for time. So time would be 2,96 divided by 9,8. And now if we use our calculator, remember we stored our answer there. Let's just check again if it is what it is. Yes, it is. So I have my answer divided by 9,8. And I have 0,3. 30 seconds. That was just the upwards motion. Okay, we need to then look at the downwards. Okay, let me not hide it too much. Okay, again, I'm still going to use the same formula. My final velocity, I have it at 62,68. My initial velocity is 0 plus, okay, so final velocity 62,68. Initial velocity is 0. And because now it's going down, well, it doesn't matter because the initial velocity is 0 in any case. And yeah, so now time would be 62,68 divided by 9,8. Okay, so we have 62,68 divided by 9,8. And then the answer there is 6,395. If I round it up to 2 decimal places, that will be 6,4 seconds. But I'm going to also store this answer just in case. Okay, so let's just check B. So A is 2,96 and then B is, yeah. So now the final time, guys, that it took for stone A to reach the ground, or total time, not final time. So the total time would be 0,3 plus 6,4. Okay, so I'm going to take A, no, I didn't save the 0,3. I didn't save it. Okay, shift, store, C. Okay, so I have then B plus C, and that gives me, no, something is wrong. This is 6, that, and then C. Alrighty, sorry guys, I'm taking a while here. But yeah, I just want to make sure that I don't really use rounded off values. Okay, so I then have B plus C. Okay, then I have 6,698, blah blah blah. So it's simply 6,7. Okay, so that is the time it took for stone A to reach the ground, or to strike the ground. Okay, now let us see 3.3 or 3.2.3. Okay, so 3.2.3. So now they want us to calculate the distance between the hot air balloon and stone B at the instant when stone A strikes the ground. Okay, so upon reading it initially, you're thinking, how am I going to start? For me, it's better when I illustrate things so that I know what's going on. Okay, so firstly, for me, I'm asking myself, where is stone A, where is the hot air balloon when stone A reaches the ground? That's what I would like to know first. Then I would like to know, where is stone B when stone A reaches the ground? And then once I have those locations, then I can subtract and then see how far the hot air balloon was from the stone B. But now, yeah, how? So if I were to draw a sketch for myself, so initially, okay, let's start with the hot air balloon. Ne? So we have the hot air balloon. Okay, so something like this thing is throwing an ice cream. Okay, so we have a hot air balloon there. Ne? When stone A was thrown, it was 200, ne? But I mean, when stone A eventually reached the ground, it wasn't 200 anymore. So this is stone A. Okay, initially we had 200 meters, but it went all the way up and it reached a certain height that we don't know. Okay, and then that combined height, I just want to know where, like what that amount or what that number is. Okay, so at the same time, where is stone B? But to get stone B, it's a little bit tricky. First of all, I need to know, because all of this happened, ne? Once I get this amount here, all of this happened at 6.7 seconds. But remember, stone B was thrown out after 5 seconds that stone A was thrown out. Not thrown, dropped. Yo. So after 5 seconds after stone A was dropped, then stone B was dropped. Okay, so yeah, so 1 second, 2 seconds until 6.7 seconds, and then after that 5 seconds. So we had the hot air balloon somewhere here, ne? Okay, there's a small drawing, but yeah, you get the point. So we had the hot air balloon here, and then we were dropping basically stone B. So I'm just gonna say this is B initial. Okay, stone B initially, and also this was like the hot air balloon initially, and this was the hot air balloon at the end, okay, of 6.7 seconds. So here where B was initially, I just want to know as well how far that value is, okay, from A. Or not really, I just want to know after 5 seconds. Okay, so basically after 5 seconds, where was B exactly? 5 seconds, where was B? And then at 6.7 seconds, where was B? B probably somewhere here. So we have B final. Okay, and then here the height of stone B initially, as well as the balloon, should be the same. So that's pretty much like our reference point here. So where exactly is this height here? Okay, so this is at 5 seconds now. So I want to know, where is this hot air balloon at this point? Maybe we don't need to know that, but I'm just thinking offhand. So if I know now this height, okay, of the hot air balloon, and I also know this height of stone B, then I can definitely get the difference between the two, and then I can get my answer. This is my plan. I hope I didn't lose you. So let's put values here. Okay, let's start putting values. So I'm gonna start with here, the hot air balloon. Where was it when stone A reached the ground? So I'm gonna say balloon at 6.7 seconds. Okay, now which formula are we going to use? Remember that the hot air balloon is not affected by, or rather it's not in free fall. We've already defined that for the first question. It's not in free fall. The gravitational acceleration is not the only force acting on it. If I could say, there are many other forces. Okay, so normally what you would use this equation, right? If you want to get the height, where you have that, I don't know these equations off by heart, but I think this is okay. But because we're dealing with the balloon, we can't really we can't use G. Okay, we really can't. So actually this term falls away. Okay, and on your calculation sheet you actually have this formula where it says V1, or maybe V initial and V final over 2 times time. Remember, this hot air balloon is moving at a constant speed, so V1, or rather V initial, V final, it's all the same. So if you're getting the average of it, it's just the same. Okay, so I'm just going to say it's just V times delta T. Okay, so now let's see. I chose downwards as positive, so if anything goes up, it must be negative. And I know that it's moving up at a constant velocity of that 2.96, right? And the time, well, it's 6.7 seconds. So we need to then see. Okay, so remember I stored some values. Okay, B plus C gave me the 6.7, right? I'm just gonna store this value. Shift store D. Oh, I'm storing a lot of things. Okay, and I know that A was my 2.96, right? Awesome. So if I say negative A times d. Ne? So I get negative 19,85. Okay, so it means then this value here is 19,85. I'm just going to write it down in green. So it's going up, hence there's a negative. It shows that it's from that reference here, 200. I get it? Initially, before anything happened, before stone A was dropped, it was 200 meters above ground. So then it moved up 19,85 meters. Okay, and if I take this 19,85 meters and I add it with this 200, I want a positive answer. Okay, I'm gonna add it 200. So that is just 219,85. That is when stone A reaches the ground, the hot air balloon is 219,85 meters above ground. Okay, great. Now where is B in all of this? So where is the hot air balloon when B was about to be dropped? Well, the hot air balloon, this was just after 5 seconds. So I'm still going to use this equation, negative 2,96 times 5 this time. Okay, so I'm going to multiply this by 5. And I get negative 14,82 meters. Okay, I'm just really going to round off this time. I can't be storing everything. So the hot air balloon at this point in time, this distance here was 14,82. This is as stone B was about to be dropped. Okay, so yeah, that's 14,82, meaning the height of the hot air balloon above the ground when stone B was about to be dropped, it is actually the 200 plus 14,82, so that's 214,82 meters. Okay, great. Now where is stone B relative to this? Okay, so since stone B was dropped 5 seconds after stone A was dropped, where is stone B at 6,7 seconds? Well, I can tell you this, or rather, how long was stone B in the air when stone A reached the ground? Stone B was in the air for 1,7 seconds. Okay, so I want to know, where is stone B at 1,7 seconds? Geez, I hope you're really following. I really hope you're following. So we're gonna now use that other formula. I can't use this formula here, V times delta T. I can't use this. Remember this V, that's a V average. Okay, it was taken from V initial plus V final over 2 times delta T. I don't know. I know the initial velocity of B. It was 2,96 because same story as stone A. The initial velocity will not be 0, even if it was dropped, because there's a hot air balloon busy moving up. Its initial velocity will be the same as the velocity, or rather the speed of the hot air balloon. So I know the initial, but I don't know what the final velocity is at 1,7 seconds. So I'm not going to use this formula here. Okay, it's going to just mess me up. I'm just going to use the formula where I just need initial velocity. So it's initial velocity times time plus half g delta t squared. I hope this is the right equation. Okay, so the initial velocity, again, stone B also followed that parabolic trajectory. Okay, so it's gonna go up a bit, and because it goes up, we use negative 2,96, and then the time it took for that whole motion, or rather the time we're interested in, that is 1,7 seconds, and then plus half, G is always positive because we took down as positive, and then you get 1,7 squared. So let us see what that value is. Okay, so we have negative A times Okay, so we know that D was that 6,7 minus 5. That's how we got the 1,7. Okay, and then plus half times 9,8. Okay, times, again, I'm just going to take 1,7 squared. Okay, and we have 9,1 exactly. Okay, so 9,10 meters. On our sketch, where is 9,1? Remember, downwards is positive, so 9,1 is this one over here. Okay, 9,1. Maybe let me use a different color. Okay, let us use black. So this distance over here, it's 9,1 meters. Okay. So do we have all the values that we need? Let me use a red color. Do we now have all the values that we need to then get to our answer? So this is, B is 9,1 meters from this reference point at 6,7 seconds. Ne? And then we know that the hot air balloon, so the hot air balloon is at 219,85 meters. Okay, and we know that B, so our reference point here, let me put it down in green. Our reference point here is actually 214,85 meters. Okay, and B, it is actually 2,14 minus this 9,1. Okay, let me see. Did I have that 2,14? No, it's out. I removed it somewhere. Okay. So 14,81 plus 200. Okay, so 2,14 minus 9,1, I get 205. So B is actually at 205,72 meters. And now, finally, we can answer. We know where B is relative to the ground at 6,7 seconds. We know where the hot air balloon is relative to the ground at 6,7 seconds. So now we have the elevations at 6,7 seconds, right? Now we can then get the difference. Okay, let's just read the question again. The distance between the hot air balloon and stone B at the instant when stone A strikes the ground. Yes, we can finally calculate. Okay, so I have 219,85 minus the answer, and I get 14,13. So ekugcineni, at the end of it all, I'm just going to put it in red. So the distance between the hot air balloon and stone B at 6,7 seconds, well, that's basically 14, sorry for the background noise, someone is calling me, 14,3 meters or 14,13 meters. Okay, so yeah, we have answered that question. It took time. I don't know how you approached it. Okay, if you wrote the paper, I don't know how you might approach it if you get a question like this in the future. That's for grade 11s going to grade 12 or grade 12s that are upgrading. But for me, honestly, drawing sketches really helps because I understand where I am in everything, and then I can get my answer. Okay, for me, seeing is believing. All right, and now question 3.3. Okay, so 3.3, we are there. All right. Oh, look at me writing 3.4. Okay, so 3.3, I decided to just draw the graph so that I don't waste time constructing it. Yeah, and it says on the same set of axes, Draw position time graphs for both the hot air balloon and stone A from the moment the stone is dropped until it strikes the ground. So here's the key. Use the ground as zero reference. So that's why I've written there that this is the ground level. Okay, remember the stone, from the hot air balloon, it went something like this until it reached the ground. Okay, and the hot air balloon, Yona, it just went up straight. Okay, but we'll see how it all pans out. All right, so at time 0, they were both, let me just put 0 there. So at time 0, they were both together. Okay, so stone A and the hot air balloon, and they were 200 meters above ground. Okay, and then at 0.3 seconds, let's just sketch the stone first with blue. So at 0.3 seconds, remember when I calculated separately going up and down for the stone? So I calculate that that's going to be 0.3 seconds. It goes up a bit, and then obviously it comes back to 200 meters at 0.6 seconds. And then at 6.7, that's where it touches or reaches the ground. So let us see when we attempt to draw this, how that's going to look. Okay, this is gonna take the whole day. Okay. Okay, that is what happens. And then now, so this is the stone. Okay, stone A. Okay, and now the hot air balloon. Okay, so the hot air balloon, it moves at constant velocity. Remember the equations, well, the equation we used to get y for the hot air balloon, we used velocity times time. Okay, if you think about your straight line graph, it's basically this. So m being the velocity, that is your gradient. Your velocity is your gradient. So because the gradient is constant, okay, it's just going to do a straight line like that. Okay, and where it cuts the y-axis, you'll see value that's actually 200. Okay, so this should actually be plus 200, negative v times 200, because we took upwards as negative. But yeah, so in sketching the graph, it has to be a straight line graph. Okay, it has to start at 200. By using that equation, if you wanted to, you could get the height at t is equal to 0.3, 0.6, but we know at 6.7, I even wrote it here, at 6.7, we actually have it at 219.85, like I've shown in the previous question. So we know it is starting here at 200 and it is ending here at 219.85. Okay, and it's a straight line. So I am not going to attempt to do a straight line. I'm just going to use the ruler, because I am going to be defeated if I try to draw it. And then I'm going to try to, be perfect about it and not finish this question. So we are there at the finals and we are done. So basically that would represent the hot air balloon. And that is it. We are done with question 3. Yeah, I hope you understood. I hope I didn't confuse you with 3.2.3. But yeah, thank you for tuning in and bye.
Well, welcome to MV Tutors. My name is Fira and I'll be your tutor today. We are still doing the 2021 November Physical Science paper number 1. And we are now on question 4. So, if this is what you want to be doing, then you came to the right place. Let's get right into it. So it says a ball X of mass 10 kg is moving eastwards. So this ball is moving eastwards, okay, at a velocity of 2 meters per second. Cool. it collides elastically with another ball. That's important, elastically, because you know what that means. It means that kinetic energy before is the same as kinetic energy after. Okay, so while with another ball, y, there it is, of mass 2 kg. Okay, so the different masses. This one is 10, that one is 2, which was moving with an unknown velocity. Okay, immediately after the collision, ball X comes to rest. Okay, there it is, they showed it. And ball Y moves eastwards with a kinetic energy of 36 joules. Okay, there we go, diagram B. Explain the meaning of the term elastic collision. We've spoken about it already, that it means that kinetic energy before is the same as kinetic energy after, so kinetic energy is conserved. Now calculate the velocity of that one. Now let's just use the definitions of kinetic energy. We said let's go 4.2. We said well, the sum of the kinetic energies basically you know, before is equals to the sum of the kinetic energies after. All right, cool. So what's the formula for kinetic energy? It's basically just a half mv squared. Okay, so now here we've got 2. So before we've got 2 of them, we've got x, this is for x, plus, remember we said sum, half mv squared for y. All of this is before, all right, and then after it's gonna be the same, half mv squared x plus half mv squared y. Okay, now we can start filling them in. Half, well, the first mass of x is 10, so we put 10 there. And then for v, what is our initial mass? We have been given it's 2 meters per second, so we'll put 2 there, and it's squared, plus half the second mass we've been given, it's 2, right? And then v y is what we are looking for, so that's equals to half mass, this is the mass of x, which is 10, and afterwards, you know, velocity is 0, so we got 0 squared there. Cool. Plus fortunately here we've been given that it's just 36. Remember they said it moves, ball y move eastwards with a kinetic energy of 36, so I'm just gonna put it there. It means they've already calculated that kinetic energy there, and it's 36. So now all that's left is just to do some mathematical gymnastics. All right, so what I want to do then is that I'll keep v squared this side, and then 36, I'll take this is 10 divided by 2 is 5 times 2 squared, 2 squared is 4, that's 20, so that's minus 20. Okay, and here for this one it's just 2 divided by 2, which is 1, so it stays like that. So I have 36 minus 20, so that's gonna be v squared is equals to 16. So v is then, because if I square root both of them to get rid of that square, I'm getting plus or minus 4. So our final answer then, remember they said it's moving, so it's either it's moving forward or backward, but it's moving at 4 meters per second. So I'm just going to say v is equals to 4 meters per second. But remember, velocity is a vector, so it needs direction. I have to choose whether it's going this or that way. Okay, but I'm going to say it's going west, the opposite direction, because the only way this can stop is if this one is going the opposite direction, which is west. Okay, think about it. If it was going east as well, it wouldn't stop, it wouldn't come to 0. Okay, so it's definitely going west. Cool. The next question says calculate, the balls were in contact with each other for 0.1 seconds during the collision. Calculate the magnitude of the force that the ball X exerts on ball Y during the collision. Okay, so we are going to use impulse factors here. All right, so we're just gonna say, let's choose a different color. This is now 4.3. We're gonna use the formula F net, that's the impulse times change in time, is really equals to the change in impulse. All right, and then okay, so let me do this then, just to complete it. F net, which is the force we're looking for, is just gonna be change in impulse over change in time, right? So what's our change in impulse? Okay, first of all, in terms of formulas, we know that actually impulse is given by m times mass times change in velocity over change in time. So the mass, we're gonna use the mass of x, which is 10, and then its change in velocity. It started off okay, the change in velocity, okay, let me just put this further. The changes in velocity is velocity final minus velocity initial. Okay, and that's still changing time. So the final, it ends up at 0, right? Minus, but it started, or initially it started at 2 meters per second. And then divide that by the change in time, which we've been given already, is 0.1. Okay, so we'll need a calculator for this one. I'll put it exactly as it is. So I'll put 10 times 0 minus 2, close that bracket, come down here, I'll put 0.1, and I get minus 200. Minus 200 newtons. That's the force, the magnitude of force that ball X exerts on ball Y. Okay. Yeah, let's leave it at that. F net is that. Okay, that's it. So if there's something you didn't understand, I'm available to tutor you. Just contact me on my email address, which is www.mvtutors.co.za, or alternatively you can WhatsApp me on 076 312 1107. And before you contact us, please make sure you involve your parent or your guardian, because remember, at the end of the day, they are the ones who are going to be paying for your tutoring sessions. So before you contact us, make sure you speak to them first. Okay, Well, that's it from me. I hope you understood and I appreciate you. Good day to you. Welcome to MV Tutors. We are now doing the November 2021 physical science paper 1. We are now in question number 5. So that is what we're doing. If that's what you're looking for, then you came to the right place. Stick around and we're gonna set it off. All right. So question 5, if we look over here, question 5, let me just zoom in a bit. Okay, it says that a 2 kg box is released from rest at point P over there, 5 meters above the ground. Okay, I see that. It slides down a smooth frictionless curve PQ. So okay, see diagram below. Okay, and then it says states the principle of conservation of mechanical energy in words. Okay, oh goodness, there's a fly over here. We're still out in the jungle here. So there's a lot of animals going on around, including flies, mosquitoes, buffaloes, impalas, hippos, like ostriches. They're here, all of them, you know. But anyway, conservation of mechanical energy. Well, it's just simple. You know, mechanical energy in a closed system remains constant. Okay, so that means potential energy plus kinetic energy before is equals to potential energy plus kinetic energy after. So mechanical energy before is equals to mechanical energy after. Okay. Now it says use the principles of conservation of mechanical energy to calculate the speed of the box when it reaches point Q. Okay, let us do that. Start with the black. So we were saying mechanical energy. So mech before, you know, is really mech before is really equals to mechanical energy after. Cool. So what is mechanical energy? It's start with potential energy plus kinetic energy before is really equals to potential energy plus kinetic energy after. Okay, so potential energy is given by mgh, kinetic energy is half mv squared, same this side, mgh plus half mv squared. Remember, the side is all after. So now let's start filling up. The m, that's the mass, that's going to be 2. G is 9.8. H before is 5 plus a half. M is still 2. No, I don't want to circle. And then V, it says it's at rest at point P, so that's gonna be 0. That's gonna be equals to M, that's still 2. Gravity is still 9.8. And then H at Q, we're not at after now, is Q. So Q is at Q it's 0 plus a half. M is still 2, and then V, what's the velocity there? Is that what we are perhaps looking for? Yes, velocity squared. Cool. So let's get a calculator. Okay, so first one is 2 times 9.8 times 5, so that gives us 98, plus this one is 0 because it's multiplied with 0, is equals to, this one is 0 as well because it's multiplied with 0, then this one is plus v squared, and now what I really have is 98 is equals to v squared. So to get v square root both of them, therefore my final velocity is equals to, let's just say, square root of 98, and then in terms of decimals, that's about 9.9. so that's 9.9. Let me move that little line. It's 9.9 meters per second. Okay, so that's the velocity, and it's positive, so it's going to the right. Should I say right? Yeah, let's say right. Okay. All right, now let's go to the next question. The box passes point Q and moves 10 meters on rough horizontal surface. Okay, I see there as it's demonstrated all over there. Then what happens? Before striking a barrier at point R at a speed 4 meters per second. Okay, so it's 4 meters per second there. Use energy principles to calculate the magnitude of the average frictional force acting on the box as it moves from Q to R. Okay, no problem. Let's do just that. So about that. I'm gonna change my color. Let's make it red. So we are now question, what's this, 5.3. Okay, cool. So what we have here, what we're gonna use work is equals to change in really it's just change in mechanical energy, or change in kinetic energy rather. That's work, change in kinetic. It should be in your formula sheet, but also work is also equals to you know, it's equals to force times change in distance times cos theta. So what I'm going to do is just combine these two, okay, and hopefully I'll solve for the frictional force. Okay, so let me combine those two. So I'm gonna say change in kinetic energy, or change in K. Let me be consistent, put the K down here, is equals to force times change in distance times cos theta. Okay, so what's my EK? EK is change in kinetic is half mv squared, that's the final one, minus half mv squared, that's the initial velocity, still equals to f change in x cos theta. Okay, so let's start filling in the numbers. The mass there is still 2. The final velocity, we have it is 4, right, squared minus a half, that's still 2, and then the v, the initial one, is the one we just solved there, which is 9.9 squared. That's gonna be equals to the force. Now what's the force? Now if we look at this object, we look at the forces, it only, there's nothing pushing it that way, but it's moving on a direction of the right. So friction is the only force acting on it, friction force. Okay, so then that force there is going to be the friction force, right? And then the change in distance, that's the 10, and then cos, theta is always equals to the direction that the object is moving towards, which is right, and then the force that you are working with. So it's 180 in this instance, because from there to there is 180 degrees. Okay, now we're just gonna do some gymnastics. Let's bring back our calculator. I'm gonna say, okay, that's a half, right? A half times 2, that's 1, so it's really just 4 squared. 4 squared minus, also here we have the same situation. It's gonna be 9.9 squared, and then that's gonna be equals to minus 82.01 is equals to friction force, and then I want to divide it by that. Okay, 10 cos 180. Okay, so I'm gonna say divided by, let me put it in a bracket, 10 cos, where's cos 180. Okay, cool. And what's this equals to? 8.2. So I can conclude then and say the frictional force is equals to 8.2 newtons. And which direction is it going on? It's going, the reason it's negative, because it's gonna be negative, but we'll write it positive, and then we'll just say left. Okay, that's it. Right, let's go now to the next question. Next question says the barrier exerts an impulse of 14 newtons per second to the left on the box when the box strikes the barrier. Calculates the change in kinetic energy of the box after striking the barrier. Okay, so they want kinetic energy, right? So what do we know about kinetic energy? This much we know. This is now 5.4, right? It's 5.4. So kinetic energy, really, the change in kinetic energy, kinetic, is equals to kinetic energy final, right, minus the kinetic energy initial. So what we're gonna do then is that we're gonna substitute and see what we have. So that's half mv squared final minus half mv squared initial. So that's a half. M is still 2, it's the same box, and then our final velocity, they gave us the impulse, so I think we pretty much have to solve for it, but our initial one, we know that our initial one is 4, so we have to solve that one. Let's actually go to the side and solve it first. Okay, so we're gonna use impulse equations to solve for this velocity. Okay, we're gonna say we know that impulse is force times change in time is equals to like the change in impulse. So and we know that the change in impulse is also equals to mass times the change in velocity. Okay, so we're going to put these together. Okay, so far what is it that we do know is that oh actually uh, we have been given the change in impulse in this question. Exerts a force of 14. Okay, so I'm just gonna rewrite this formula and say change in impulse. I'm gonna write these two together, equate these two is equals to m times change in v, because both of them are equals to force times change in time. So impulse I've been given as 14, and then mass is still 2. Change in velocity, now I have that it actually, the final one is the one that I'm looking for, minus the initial one is 4. Okay, because we told it hits it at 4. When it hits here, it hits it at 4, and then when it goes back, that's the one we're trying to investigate. So we'll put 4 there. Then do some gymnastics. 14 divided by 2, that's 7, is equals to Vf minus 4. If I take minus 4 this side to the other side, okay, now we need to be actually very careful here, because this 14, it said it's 14 to the left, and to the left is actually a negative number because right is positive, right? So it's minus 7 there. Okay, so then when I take this to the other side, then Vf becomes what? It becomes minus 3. You see that? So which means when I come back here under Vf, I'll just put minus 3 squared minus half 2, and then the initial one is still 4 squared. And I just have to put this in the calculator. So this half and 2, they cancel each other, so I'm left with 3 squared. Doesn't matter whether it's negative or not, it's still gonna, the answer is still gonna be positive, so might as well put it like that, minus 4 squared. Okay, and then I get my answer is minus 7 joules. That is my final answer over there. That's my change in kinetic. Sometimes I like writing it that way, in kinetic energy. Good, that's all. Well, I hope you understood, but in the event that you didn't, I'm available to tutor you in these matters. Please do contact me on my website at www.mvtutors.co.za, or alternatively just WhatsApp me on 076-312-1107. I mean, visit my website. That's my website I gave you first. Other than that, please make sure that before you contact us that you speak to your parent or your guardian, because remember, at the end of the day, they're the ones that are going to be paying for my tutoring services, so they need to be involved in the decision making. Other than that, I hope you understood. That's it from me. Enjoy the rest of your day, and I appreciate you. Welcome to MV Tutors. My name is Fia and I will be your tutor today. So, we are doing the 2021 November final examination. This is Physical Science Paper 1 and we are on question number 6 now. So, this is what we'll be doing. If that's what you want, then stick around, and by the end of this session, you'll be able to understand everything. Well, let's get right into it. Question 6. The siren of a stationary ambulance emits sound waves at a constant frequency of 680 Hz. A man is standing with a detector that records the wavelength of the sound emitted by the siren, as shown in the diagram below. Okay, the speed of sound in air is 340 meters per second. Now calculate the wavelength of the detected sound. Okay, so what do we need here? We need the formula to calculate this speed. The speed formula, if you know it, 6.1, you know that velocity is equals to frequency times the wavelength. Okay, so the velocity, have we been given the velocity? We have, there's the speed of sound. It's the speed, so it's 340 equals to the frequency. Have we been given the frequency? Let's see, there it is, frequency of sound 680. So we've got 680 and then the wavelength over there. And what do we want to calculate is the wavelength, so we will therefore the wavelength is equals to 6. Okay, to get rid of this 680, divide both sides by 680. Okay, and then we need to bring in a calculator so that we can calculate what this is. So it's 340 divided by 680. There we go, and it's exactly a half. Okay, let me put it in decimal, which is 0.5. And what are the units of a wavelength? It's a wavelength, so length is in meters. Cool. And then they say the ambulance now moves at a constant speed along the road towards the man. The detector now records the wavelength of the sound, which differs from the previous reading of reading by 0.05. Okay, states the Doppler effect. Okay, so theoretically speaking, the Doppler effect is just the change in frequency, okay, of the sound that is detected by a listener because the sound source and the listener have different velocities relative to the medium of sound propagation. Now you have to write all of that down. That is the Doppler effect, theoretically speaking. Okay, so it just has to do with a moving, source and a listener. Okay, that they move relative to each other and the velocities are different. But if you think of the Doppler effects, think of the formula as well, because one of the ways we do definitions in physical science is using the formula. So you see the formula has a velocity, it also has frequency, so just think of these two. Okay, now it says, how would each of the following have changed when the ambulance approached the detector compared to when the ambulance was stationary? So it's basically asking when the ambulance is moving, okay, what is the change? Choose from increased, decreased, or no change. Distance between the wave fronts. Okay, so what happens to the distance of the wave as they get closer? Okay, so as they get closer, actually the wave also gets smaller. So 6.3.1, it actually decreases. The wavelength decreases as it gets closer and closer. And then what happens to the frequency of uh, the wavelength? Okay, so look at this formula again. If the sound, if okay, let me just make the wavelength the subject of the formula. And then what are we looking at? The frequency. Okay, so if I make the wavelength the subject of the formula, you can clearly see that the wavelength and frequency are inversely proportional, which means if wavelength is decreasing, then the frequency will increase. So we have increase here, increases. Okay, let's do 6.4 now. 6.4. Cool. Calculate the speed of the ambulance. Okay, so we need a special formula for this. We know that the frequency of the listener is equals to the frequency of the sound, and then in brackets we have velocity plus or minus VL, that's the listener, and then we have velocity again plus or minus Vs, that's the velocity of the source. Okay, so this is the velocity of the medium, which is air in this example. So we are looking for Vs, right? Okay, so which means we need to substitute all of these values. All right, let's start with the frequency of the listener. Okay, so fortunately, remember V is equals to frequency times wavelength. So the velocity that we do have is okay, that's, what am I looking for? I'm looking for F. Okay, so the velocity of the listener, no, this is the velocity of the medium, so it's still 340, but the frequency is what we are looking for. We're looking for the new frequency, and the wavelength, that's what's gonna change. Okay, remember we solved it as 0.5. we have to subtract because you see here it says which differs from the previous reading by 0.05, so it means we must subtract 0.05 over here. Okay, and then my F is just simply gonna be 340 divided by 0.5 minus 0.05. Let's get a calculator. I'll put that, and then I'll put 340. Come downstairs, put 0.5 minus 0.05. Good. Okay, what is that? Oh, okay. So we get 755.55. So I'll make it 56. I'll just take 2 decimals. Okay, that's cool. So most of the time you take decimals at the end. So I will want to keep this as it is. But you know, it's fine. Let's move on. Okay, so this is the frequency of the listener. All right. Okay, let's go back then to our formula. Let's get more space. Okay, so our formula has FL is equals to Fs, all right? And then velocity of the medium. Now, velocity of the listener is 0 because the listener is stationary, right? He's not moving anywhere. Remember, they told us that he's just standing there. Okay, a man standing. So there's no velocity of the listener on top. And then the theory is that if the source is moving towards the listener, then your velocity you subtract it's a negative velocity of the source. If the source was moving away from the listener, then this would be a plus instead of a minus. It's a minus because it's moving towards the listener. That's the theory behind choosing that sign. Okay, so let's start filling in the numbers. The frequency of the listener is 755.56, all right, is equals to the frequency of the source. Okay, we were told here is 680. Okay, and then the velocity over here is just going to be the medium velocity, which is 340, divided by, still here it's 340 minus Vs. That's what we are looking for. All that's left for us to do now is just some mathematical gymnastics to get the answer. So first I'll divide both sides by 680. Okay, like that. That's just gymnastics. Let's get a calculator. Divide by 680. That's gonna be equals to, well, 1.11 is equals to 340 divided by 340 minus Vs. Okay, I cross multiply, I take that there, or to get rid of this fraction, multiply both sides by 3 by the denominator. Okay, like this. 340 minus Vs is equals to 340, because here it will cancel each other. Cool, then I just multiply that in and there. So first times 340, and then I get 377.78 minus 1.11 times Vs is equals to 340. Okay, what do I want to do? Let me take this to the other side so that I'll be left with minus 1.11 Vs is equals to. So now what I want to do is that it's gonna be, sorry, I have to get rid of this now. Okay, so it's gonna be 340 minus 377.78, and then we get minus 37.78, and then finally divide both sides by minus, so Vs by minus 1.11. So I'm gonna say divided by negative 1.1111. There was a lot of ones. So my final answer is just 34. And velocity is in meters per second. Okay. All right, so that's it. That's it. I'll just leave it there. I will leave it there. Um, oh, velocity is a vector, so I will say towards the right because it's moving towards the right, as you can see from the picture. Okay, that's it. Well, I hope you understood, but in the event that you didn't, I would love to be your tutor. So do contact me via my email, which is www.mvtutors.co.za, or alternatively, you can just WhatsApp me on 076 312 1107. And before you do contact me, please speak to your guardian or your parent. Just make sure you involve them in the process, because remember, at the end of the day, they are the ones who will be paying for the tutoring services. So other than that, thank you so much. I hope you understood, and I appreciate you.
Hello everyone and welcome to MV Tutors. I'm Solo and I'll be looking at question 7 with you guys. Yeah, guys, please subscribe to our channel and like our videos. Those who are in matric, well, you guys are done already. You're probably not interested at this point, but for the future matriculants of next year, please just spread the word to the grade 11s who are going to be in matric next year doing physics, and also for the matrics who are going to be upgrading next year. And maybe you felt like these papers were difficult, so you want to upgrade so that you can get into the courses that you would like to do. Please just share this with those people, and yeah, let's share, guys. Let's share knowledge, let's share information and get it out there and pass. Okay, so looking at question 7, yeah, electrostatics. It says a small neutral sphere acquires a charge of negative 1,95 times 10 to the power minus 6 coulomb. Okay, so let's see, 7.1.1. Were electrons added to or removed from the sphere? Okay, so initially the sphere was neutral. Okay, if this sphere was neutral, it was at 0. Okay, if it ended up being negative, that means that you added electrons. Okay, so yes, in this case the electrons were added. Okay, if it went from 0 all the way to negative, electrons were added. If electrons were removed, it would be positive, because once you remove electrons, you're left with protons. Okay, so I hope it makes sense. So the answer is added. Okay, what did I do now? All right, in 7.1.2, calculate the number of electrons which were added or removed. Okay, so the calculation, I don't know if they have the formula on the formula sheet. I don't have it with me now. But if you want to get the number of electrons, basically you're going to get the charge of the sphere or whatever object they've given you, and then you're going to divide it by the charge of an electron. Okay, I know that the charge of the electron is actually given in the formula sheet, but the charge that they gave us there, you have negative 1,95 times 10 to the power negative 6 coulomb. Okay, and the charge of an electron, if I remember correctly, it is negative 1,6 times 10 to the power negative 19. Okay, yes, it is. I just confirmed. And yeah, let us see. So we have negative 1,95 times 10 to the power negative 6 divided by negative 1,6 times 10 to the power negative 19. Okay, and then you have how many electrons? We have 1,22 times 10 to the power 13 electrons. That's basically the amount of electrons that you have. Okay, this was a very nice question. Okay, and then 7,1,3, define the term electric field at a point. So this is where you guys need to know your theory. So electric field at a point. If you by any chance forget your definitions, go to your formula sheet and go and have a look at the formulas. Okay, so for electric field, for one, the formula given there, so E, that would be the force per unit charge. Okay, so yeah, F over Q, or maybe let me use big Q. Okay, so define the term electric field at a point. So the electric field at a point is where you have your net electric force. Okay, and it, yeah, basically it would be the net electric force per unit charge. That's how I would put it. Okay, or yeah, so it'd be electric force per unit charge. Oh, okay, the one thing that you shouldn't forget. Okay, so let me just write it down. It would be the electric force per unit. Okay, now the keyword here, positive. Positive. Okay, let's just write it properly. Per unit positive charge. So the electric field at a point is the electric force per unit positive charge experienced, if you want to go deeper, at a point in the electric field. Okay, but the equation, guys, it will help you, especially if you forgot the definition. You know, okay, this is force per charge, but that charge is positive and it's all happening in the electric field. Okay, cool. So 7.1.4. 7.1.4, calculate the magnitude of the electric field at a point 0.5 meters from the center of the charged sphere. Okay, so here we already have our formula, right? We know that E is F over Q, but remember that F is equal to K, Q1, Q2, all over R squared. Okay, so if we put this equation in there, one of the Q's is going to cancel out. So you have small k, 1Q, all over R squared. Okay, so that is E. So what is K? The constant would be 9 times 10 to the power 9. And the charge that we have there, we're not going to consider, because we said positive charge, we're not going to put the negative sign there. We know that we have 1,95 times 10 to the power minus 6. Okay, and that is all over R squared. They gave us, it is 0.5 meters. So just 0.5 squared. Okay, you can calculate that. So we have 9 times 10 to the 9, then we multiply it by 1,95 times 10 to the power minus 6, and that is all over 0,5 squared. And our answer is 70,200. And what is the unit? Because you have force per unit charge, it's going to be Newton per Coulomb. Oh, actually, it's actually written like this. Yes. Okay. And then 7.1, no, 7.2. Okay, we're getting there. Okay, 2-point charges Q1 and Q2 are fixed 0,02 meters apart. The magnitude of charges Q1 and Q2 is the same. Okay, we know that Q1 is negatively charged, they told us, but we don't know the charge of Q2. So don't be quick to assume that it is positive. We don't know. Now it says the small charged sphere with the charge of negative 1,95 times 10 to the power minus 6 is placed at point P. Okay, as you can see, this is where point P is. which is 0.03 meters east of Q2, as shown in the diagram below. The sphere at point P experiences a net electrostatic force of 1.38 Newton west. Okay, so here we have Q1, ne? We know that it is negative. Okay, so it's actually, it's a negative charge. And you know, with a negative charge, if you were to draw electric field lines, you know, they all go in. Okay, then you have Q2. We don't really know the charge there. And then we have P. Okay, so we have a sphere here as well. We know the charge there is negative. Okay, so again, you know, if you were to draw the electric field lines, they're all going in. Okay, and then they tell you guys that okay, so we already know the charge there, right? It's negative 1.95 times 10 to the negative 6, but they tell you that the net electrostatic force is 1.38 west. So west is this direction. So we have 1.38 Newton. So I'm going to take west as negative. Okay, so if they say west, then it's negative. And now we need to get the magnitude of Q2. So they don't want necessarily the direction. It's mainly to do with the magnitude. But so if your net force is west, so you can see that Q1 and P, they're both negative, meaning they repel one another. Okay, so yeah, if you were to draw them side by side, they would be like doing something like that. Okay, but obviously with arrows pointing inside. Yeah, they're pretty much repelling each other. Okay, so if the net, okay, anyway, they told us it's west, the net force. Okay, the electrostatic force is 1.38. Now these two are repelling each other, right? So maybe you have then a force. I'm just gonna take this side. You have a force here going to the west, right? And on the other side, you have a force, basically Q1, going to the east. Okay, what would this one be for you to have everything, or rather the net, going to the west? It would also have to go west, right? And okay, so that the net charge can can go to the west. And yeah, so we would have to then calculate what that magnitude would have to be. Okay, but by virtue, if this was also negative, I mean, everything would be repelling each other. So just by looking at this being negative and that being negative and repelling, I would assume, but I said we shouldn't assume, our calculations would actually show us, but I would assume that this is positive, and if you were to draw the electric field lines of it being positive, then they would all go out, because that's basically what happens. Yeah, and in this case, it would go west, but yeah. Okay, so now let us calculate. And because they told us about the net electrostatic force, we're going to calculate for the force first and foremost. Okay, of Q1, okay, and P. All right, so we have Q1, I'm going to say QP, all over R squared. Okay, so we have 9 times 10 to the 9, and then Q1, we don't know what that is. Okay, and P, well, that is 1.95 times 10 to the power negative 6, and then the distance in between them will be 0.05. Okay, and then we have Q2 due to P. All right, again, we're gonna have 9 times 10 to the 9. I'm not gonna write the formula again. This time we have Q2 and same story, 1,95 times 10 to the power negative 6. And the distance between Q2 and P is 0,03 squared. Okay, so if we work that out, well, here we have 9 times 10 to the 9 times 1,95. Okay, so here this answer is going to be 70,200 Q1. Okay, remember it's going to be in terms of no. You see, here we have 0,05. Yeah, so yeah, that makes a big difference. So let me just erase that. So 7,020,000. Okay, and that would be the force, which is Newton. And don't forget the Q1. And then on the other hand, we have 0,03. So that would be 3, 6, oh, what? 19 million. Okay, so that's quite a lot. And 500,000. Okay, and that's also in terms of Q1, I mean Q2. All right, and that's Newton. Oh. Okay, so the net force that we have. Oh, one thing before we get to the net, they told us that Q1 and Q2 have the same magnitude, okay? But by looking at our diagram over there, it goes in different directions, okay? So Q1 is actually equal to Q2 when we talk about magnitude, not necessarily direction, okay? So therefore, I would say then the force of Q1 to P, no, let me rather just say Q1 is equal to Q2, so therefore I'm going to make it equal to Q once. Okay, now we have F net. So net force, we have force of Q1 due to P plus the force of Q2 due to P. The net force is already waste, so I chose waste as negative, so we have negative 1,38. And then we said that Q1 will actually go east. Okay, yeah, so, and if you're not sure why that is, if you have a look at this, because they repel each other, when one goes west, the other has to go east. Okay, yeah, they're not gonna get together. So this is like pointing to the west, this will be pointing to the east type thing. Yeah, so they're doing opposite things. Okay, yeah, so Q1P, so that's definitely going to the east, and that would be 7 million. Okay, and then because the net force is actually negative, it means that the force due to, well, Q and P, okay, that will contribute to it being highly negative, if that makes sense. Okay, so this one had to be negative in this case, it had to be waste. Okay, so for that we have 19,500,000. Okay, and that's Q, I forgot the Q. Okay, so if I then have 7,020,000 and I subtract 19,500,000, I am then left with negative 18,798,000. No, what am I left with? I think I put too much there. 19,500. Okay, I don't know, but this should be 18,798,000. Yeah, this should be that. What did I do up there? Okay, so we have 7, 1, 2, 3, and we have 19, 1, 2, 3, 1, 2, 3. Oh, I added an extra 0. No wonder it looked weird. No wonder. Okay, let us erase that. Okay, I pressed too many zeros. Okay, so it's negative 1,248,000. No, 12 million. Yo, guys, what's happening with me today? I'm now pulling a Jacob Zuma on you guys. Negative 12,480,000. Okay, and that's still Q. That's negative 1,38. So ultimately, what the charge on Q is, you will get 1,38 divided by 12,480. 1, 2, 3. Negative, negative. Okay, so we have negative 1,38 divided by the answer, and we have 1,11 times 10 to the power negative 7, and because this is charge, this would be coulomb. Okay, all right, so yeah, that is the magnitude. They didn't ask for the direction, and I believe we are done. So thank you for tuning in, and like I've said, please spread the word to those who are in need of this precious information. Hello everyone, and welcome to MV Tutors. I'm Sulu, and I'll be looking at question 8 with you guys. Please don't forget to like our videos and subscribe to our channel. Visit our website if you wanna. If you need extra tutorial sessions, you can book a lesson there. If you're in grade 11 this year, this is 2021, please make sure that you're subscribing for next year, okay? And also, if you are going to be rewriting or upgrading your matric, this is the place to be, okay? We are sorting you out via maths and physics. But let us have a look at question 8 for our paper 1. So it says the battery in the circuit shown below has an EMF of 12 volts and an unknown internal resistance R. The resistance of the connecting wires and the ammeter is negligible. Okay, so you can see here our EMF is 12 volts, the internal resistance, and. Okay. So 8.1, it says, write down the reading on voltmeter V1. So this is voltmeter V1, and it is across the battery. Okay, so when switch S is open, the voltmeter across the battery will be equal to the EMF. There is no current flowing, okay? As soon as there is current flowing, you do get some lost volts, all right? And then that V1 won't be 12 anymore. It will be something much less. Or not much, but it will be a little less, okay? But switch S is open, so the reading on voltmeter V1, that is 12 volts. And if you look at other okay, well, there's only voltmeter V2. But because there is no current when switch S is open, so 8.1.2, voltmeter V2 will be 0 volts. Okay, remember V is equal to IR. So there is no current flowing because switch S is open. Okay, but as soon as it is closed, you will get a reading, and V1 won't be 12, it'll be something less. Okay, now they tell us that switch S is closed, so that changes things. There's current that's flowing, V2 will have a reading, and we are yet to see how that actually changes. So it says now, switch S is closed, okay? The reading on the ammeter is 1,2 amperes. And the power dissipated in resistor X is 5,76 watts. Okay, now define the term power. Like I said, when it comes to definitions, if you have forgotten what power is, go to your formula sheet. Okay, power would be W over delta T. So basically power is the work done, or the rate, yes. As soon as there is time there, you can say power is the rate at which work is done. And you can leave it at that. Okay. Cool. Now 8.3. It says calculate the resistance of resistor X. Okay, so we've defined what power is. So we gotta use power somewhere. Okay, so power, there are like various formulas for it. First of all, it's equal to V times I. Now, I do not know the voltage across resistor X. So I'm going to change V. Remember I said V is equal to IR. So I'm going to write V in terms of, what can I do? How can I change it now? I could say R is equal to V over I. Or I could say I could write it in terms of I, but that's going to be V over R, which I have neither. Okay. Thing is, I have power already. I have the current. Oh, I'm looking for, oh, I'm complicating my life. Yes, I'm going to write it in terms of I. No. Why am I confusing myself? This voltage here, I can write it as IR, actually. Sorry, for a moment there, I was like, what am I doing? Okay, so let me not complicate my life. So basically, I squared times R, because I'm looking for the resistance. So if I put everything in terms of R, you're getting lost in your own calculation. Sorry about that. So R would be P over I squared. Okay, and what's the power? They've given it to us. It's 5,76 watts, and our I is 1,2 amperes, and that would be squared. Okay, and then if we use, here I'm looking for my calculator here. I forgot we have a calculator right there. So 5,76 divided by 1,2 squared, and that gives us 5,76. That gives us 4. Okay. So that is 4 ohms. So we know that there by X we have 4 ohms. All right. Now it says calculate the total external resistance of the circuit. So basically you have 4 ohms here, then 6, then 2,4, then 6. So I'm going to break it apart in sections. So 8,4. So I have with me 4 ohm, and then I have 6 ohm. Okay, I am going to, you see 2,4 ohms and 6 ohm, they're actually in series, so you can add them up. Okay, so this is where I am. So I have 4 ohms here, I have 6 ohm there, and then I have 8,4 ohms. So now these two are in parallel. Okay, what am I going to do with parallel resistors? So I have 1 over R parallel is equal to 1 over 6 plus 1 over 8,4. Okay, so I have 6 times 8,4, and there on top I have 8,4 plus 6. That's just pretty much cross multiplying. And then if I were to get R parallel, that would be 6 times 8,4 over 8,4 plus 6. Okay, and if we work it out, I have 6 times 8,4 divided by 6 plus 8,4. I think there is a formula like that given. So then we have 3,5 ohm. Okay, so now my sketch, I have 4 and then I have 3,5, and I have 4 ohm. Okay, so the circuit now looks like this, and I have my battery. Okay, and then I have my internal resistance. And that's it, it's a simplified circuit. Okay, you have your voltmeter 1 day. Okay, we're not even going to do voltmeter 2, but this is a simplified circuit, and ultimately the total external resistance would be 4 plus 3,5 ohm. That would give you 7,5 ohm. So it's 4 ohm. That will give you 7,5 ohm. Okay, so yes, we have that. And now it wants the reading on voltmeter V2. Okay, guys. So yeah, let's look at the circuit again. The reading on voltmeter V2. So this is 8,5. So I have my current flowing. This is the 4 ohm resistor. This is the 6 ohm resistor. I have the 2,4 ohm resistor, and I have the 6 ohm resistor. Horrible sketch. 4 ohm, 2,4, 6 ohm, and 6 ohm. My current that is flowing here, it's 1,2. It keeps flowing, but when it gets here, guys, it hits an intersection. It divides. And now we need to work out how much goes into here and how much goes into here. Okay, I'm gonna pause now. My child is here. We'll continue later. Okay, so yeah, where were we? So now looking at the circuit, you have a full current, right? A whole 1.2 amperes flowing, right, through the circuit. But as soon as we get to this point here, I like calling it an intersection, a portion of that 1.2 amperes has to go to the 6 ohm resistor, and another portion of that 1.2 amperes will pass 2,4 ohms as well as 6 ohms, the 6 ohm resistor. Okay, the same current is going to pass. Remember, these resistors are in series, so the same current passes through them. Okay, so how much goes where? So what I would do, let's see. So I would say I would want to know the current going through the 6 ohm resistor. So I have 1.2 as it is, okay. I have 6 ohm, and then the sum of this is basically 8,4 ohm. Okay, so I have 6 ohm and I have 8,4. That's my total resistance that this current is gonna pass through basically after this intersection. So, but a portion of it is just 6. Okay, so it's like getting a percentage basically. Okay, so you know you have 6, you have 8,4. What percentage is that 6? Okay, so if you were to work out a percentage, it would be, so 6 over 6 plus 8,4, and I multiply by 100. So it's basically 42% of it goes through the 6 ohm resistor. Okay, and if I take that 42% and I multiply it by 1,2, I actually get 0,5. So I know that the 0,5 amperes actually passes through the 6 ohm resistor. Okay, now let me use a different color for this one. Now, if 0,5 amperes goes through the 6, sorry, if it goes through the 6 ohm resistor, how much will go through the 8,4 ohm resistor? Well, basically, I don't have to recalculate this again, but if you wanted to, it will basically be 8,4 over 6 plus 8,4. And you'll find that if that was 42% passing through it, the other one would be 58%. But because I know it's 1,2 amperes, I can subtract 0,5 from that 1.2, and I will get 0,7 amperes. So 0,7 amperes actually goes through the 4 ohm resistor as well as the 6 ohm resistor. But remember, guys, they wanted the reading on voltmeter V2. Sorry about that. I'm going to continue. So the reading on voltmeter V2, so V2 is I times R. I've already seen or calculated what the current is, which is 0.7, and the resistor there is the 6 ohm resistor. Okay, so calculator, 0.7 times 6, and that gives us 4.2 volts. Okay, if they wanted the voltage across the 2.4 ohm resistor, you would have just multiplied it by 0.7. Okay, and then we're at the last question. Okay, so 8.6. And then I can give my son undivided attention. Okay, a length of wire of negligible resistance is used to connect point P to point Q in the circuit. Now, how will the reading on voltmeter V1 be affected? Will it increase? Will it decrease? Or no effect? Okay, let's see. So basically, if I look at my circuit, let me try to redraw it quick. So I have the 4 ohm resistor, the 2.4 ohm resistor, the 6 ohm resistor, another 6 ohm resistor, and then we have our battery, and we have that internal resistance. Just gonna do it like that rather. Okay, so we have our ampere here. Okay, and close it there. So across the 6 ohm resistor, we have voltage V2. Just going to draw it like this. Across the battery and the internal resistance, we have V1. Okay, so here we have 4 ohm. Here we have 2.4. Here we have 6. And here we have 6. And now they tell us that we are going to put a wire. Okay, so this is point P and this is point Q. Okay, so there is a wire here that we placed. Okay, let's read the question again. A length of wire of negligible resistance is used to connect P and Q in the circuit. Okay, cool. So we have point P and Q. Okay, now how will this wire affect the reading on V1? Okay, remember guys, when the circuit is open, or rather when the switch is open, V1 gets a reading of 12 volts because the EMF is 12 volts. Okay, as soon as the switch is closed and there's a current flowing, the voltmeter reading decreases. Okay, it's given up by this equation, the EMF equation, which is equal to V external, which is like V1, plus V lost. You're probably more familiar with I is equal to the external resistance plus the internal resistance, which is indicated by a small r. Okay, you're probably used to that, but ultimately I times R external will give you the V external, and big I plus small r will give you the V lost, so the voltage that is lost. Okay, and you know this external resistance, like I've shown you, it depends on the external voltage depends on the external resistance. Okay, because the current stays the same. Okay, so now let's see what happens to this current. You know, current flows from positive to negative. So positive is the longer side of the battery that is shown here. So this current I drew it differently actually in the previous question. So this current passes here, né? It goes there, it's still 1, 2, still 1, 2, and then it reaches an intersection. Okay, a portion of it goes there. We don't know what yet, because remember we have this wire PQ. It does make a difference, so let's not assume that 0,5 goes there and 0,7 goes there, or the other way around. So it goes there. So a portion of it goes this side, and a portion of it goes that side. Okay, and then this current here comes here. Okay, it hits another intersection. Thinking about it, do you think this current will want to go through this resistor? Remember, resistance is like, yeah, it is self-explanatory. It is resistance for that current. It's resistance to movement. So now, once the current comes through the resistor, it's difficult to go through. It's impeding its motion. If it were to go through Q and go all the way to P, like it's a freeway. Okay, this is like Q to P is like driving on the highway when people are on holiday on a Sunday. It's free, but going through resistor 2,4 is like driving on the N1 on the morning going from Pretoria to Joburg. Okay, there'll be a lot of resistance there because there's so many cars. So what do you think the current is going to do? Do you think the current is going to want to go to the 2,4 ohm resistor? I don't think so. This current is going to go this side, okay, and then go and then come out here, and then you have this current there that will come up here, and then it will go this side. So you have your 1,2 here, you had your 1,2 here, you had a portion of it going through 6. Actually, because it has sort of like removed this, short-circuited this, because now you have equal amounts, okay, if you have 1,2, the current that's going to pass here, it's actually 0,6 amperes, and the current passing here 0,6 amperes because it's half. Okay, then the 0,6 is going to go this side, and then it's going to come this side and come out, and it's 1.2. So how does that affect the reading of V1? Remember I said V1 actually is really, it's the external voltage, which depends on the external resistance. Okay, if now you take away this 2,4 ohm, your circuit is like this. You have the 4, you have the 6, and you have the 6. I don't know why I'm drawing like this. It's skewed, but maybe it's because I'm left-handed. Okay, so if you were to now get if you were to get R external, you have removed one of them, guys. Your external resistance is actually going to decrease because you've removed one of it. You've removed the 2,4. It's not going to be 8,4 anymore this side. It's just going to be 6. So by effectively reducing the external resistance, you are going to reduce the external voltage. Therefore, you are going to reduce V1, and you can do that. I've provided values here so that in your own free time you can actually do the calculations. You'll see your external resistance. I could do it, but we're over time. The external resistance is going to be reduced because you've removed the 2,4 ohm resistor, and by so doing your external voltage is going to be reduced. So yeah, choose from increase, decrease, or no effect. Basically, I've actually explained, guys, especially using this calculation for EMF and also here. So it's going to decrease. And everything that I've said in the exam, you're going to summarize it. Okay, so that's it from me. Enjoy the rest of your day, and I'll see you in question 9. Hello everyone, and welcome to MV Tutors. I'm Tolo, and I'll be doing question 9 with you guys. We're almost there. We're almost there, guys, and then we're gonna head over to chemistry, right? Okay. So question 9, a simplified diagram of an AC generator connected to a 25 ohm resistor is shown below. The coil rotates anti-clockwise. Geez, it's gonna be difficult because I think this camera is like mirror image. So if I say anti-clockwise, maybe you guys are seeing clockwise. So let me not. But you can see from there it is going in anti-clockwise rotation. Okay, now question 9.1. Name the component that distinguishes this generator from a DC generator. Okay, so what that would be is the slip rings. Okay, so for an AC generator, you have slip rings, but for a DC generator, you have a split ring commutator. Okay, so don't forget that. DC, split, AC, slip. Okay, and then 9.2. In which direction will the induced current flow in section XY of the coil? Okay, so this is section XY. Okay, you have Y over here and you have X over here. So remember, you have your thumb, okay, which basically is like the thrust, is like the force. Okay, so if this thing is going anti-clockwise, okay, if it's going anti-clockwise, it means on the XY direction, your thumb is actually pointing down. Okay, so your thrust is downwards. Okay, that is T, your thrust. And then if you look at the direction, so from north to south, it's actually going east. Let me not point. You're going east, right? From north to south, as you can see in the image, you're going east, okay? And that you would use with your pointing finger or your index finger. Is it index? Think. So your index finger is pointing there. Okay, so I'm gonna say index finger. This is your thumb. Okay. Oh, another thing, when you are doing the AC generator, the hand that you must use, guys, is the right hand. Please. Generators, right hand. Motors, left hand. So we're going to use the right hand rule. So your thumb is pointing downwards. Your index finger is pointing to the east or to the right. Okay. And then where will your middle finger be? Middle finger indicates the current. So if you have, like I said, the camera is actually inverted, so sorry guys, but this is my right hand. So if my thumb is pointing downwards and my index finger is pointing to the right, my middle finger is pointing to me. Okay, so it means the direction of current is actually from Y to X. Okay, yeah, so my finger is actually pointing to me, so I'm going to indicate that with that. It's pointing to me, so it's actually going, therefore the direction is from Y to X. Okay, yeah, I hope, yeah, I didn't confuse you there or anything like that, but it's actually going from Y to X. Now okay, what are we now? Where are we? So it says the graph below shows the output voltage of the generator for one cycle of rotation of the coil. If you're doing physics, you must be doing maths. So you know that to complete one wavelength of a sine graph, this looks like a sine graph. To complete one wavelength, this is a complete wavelength. And if your period is 360, then it would take this 360 degrees. But anyway, we're done with maths now. We're on physics. Okay, so yes. So this would be for an AC generator. Okay, and then now they ask, give or define the term RMS potential difference. So basically, this is VRMS. Okay, the definition of the root mean squared can be a little bit tricky, but here's the thing. If you look at an AC generator, okay, and let's look at this sine wave graph. Or even if we'll look, yes, the sine wave graph, ne? And this is for voltage, ne? This would be your Vmax, okay, on the positive, and that would be Vmax on the negative, okay? So if you go along this alternating current, the problem is, the reason why we use Vrms, we don't use Vmax, because if you look at Vmax, Vmax is like this temporary high power. It's not there for a long time, okay? So to use Vmax is very unstable, okay? And also you can't exactly, if you want to have what is it? Actually, let me just define the RMS before I go deep. I haven't defined, and here I am talking about things. So actually VRMS, I'm gonna write the definition as I've written it here, but I'm gonna explain it. It's just one of those things where you kind of cram, you know. But basically it's just to say that you want an equivalent voltage, and that equivalent voltage, so instead of using Vmax, you would use an equivalent voltage that is more sustainable, okay, and that will give you the same power output basically, or the same resistance, whatever. But VRMS is the equivalent DC voltage value that produces the same heating effect or power on an alternating or a changing AC alternating current. Okay, so when we say VRMS, or the root mean squared voltage, it's the equivalent DC voltage that produces the same heating effect. So when you have your AC voltage, so alternate, no, not AC, when you have your alternating current, ne? Or yeah, alternating current here, and you're looking at your voltage graph, okay, because it is alternating with time, you can't really rely on Vmax. Like I've said, it's just at that peak, and it's not what's the word? Yeah, it's just English is failing me. It's unstable. It is unstable, okay, as well as the V min here, Vmax in the opposite, negative Vmax. So basically it's just, let me say V min, not max. It's just unstable, okay. So basically the electricians were trying to look for an equivalent DC voltage. If you were to look at a DC voltage graph, let's say this Vmax here is 120, and then I have my equivalent V. So for my DC, the DC voltage is actually quite constant, so it's just a straight line, and that will give me 100 volts. Okay, because I know that if I were to use alternating current, it alternates with time. So here you have time in whatever, in seconds. Yeah. So at this point here, you have a reading, it's probably like 10, and here we're at like 60, whatever. Here we're at 80, and now we're 120. So it changes with time. And if you want to produce the same heating effect or the same power, you can't have something that is alternating. You need something that is like constant. So what is that constant value that would be equivalent to my DC, that will give me the same heating effect, and that will give me the same power? Because when I calculate power, remember the calculation for power, or the formula, power is equal to V times I. So what voltage can I use that is equivalent to a DC voltage? Okay, so people went and got the root mean squared. The root meaning, if you have values here, Like let's say that is 20, and that is 60, and that is 80, and that would be 120 as your maximum. They went and took those values, okay? So they took 20 and they squared it, and after squaring it, they took the 60 and squared it and took all these points, squared them. After squaring them, they got the mean of it, okay? So they calculated the mean, and after getting that mean, they basically rooted it. And they found that the equivalent DC voltage, which would be somewhere, let me just erase this. There's a formula there in the formula sheet, but it would be somewhere here. Okay, and that would give you 100 volts. And that's basically the root mean squared. They took the squared, then the mean, and then they rooted everything and they get 100. So that's why VRMS is the equivalent DC voltage value that produces the same heating effect or power on a changing alternating current. Okay, because it's alternating, we can't trust it. We can't take the peak values. Okay, we can't even take the average value, because average would be minimum plus your max over 2, and that would give you 0. So the one thing you can take that is actually stable, one thing that you can use that is stable, I guess stable is the right word to use, would be the RMS value. Okay, so I hope that you guys understand it much better. I hope, I took some time off here, but I hope you can understand what the VRMS or the IRMS is. Basically taking your equivalent DC because you want to attain the same power. You can't use something that is alternating because it gives you a different power every time. Okay, but you want something that is constant, and they calculated it, worked it out, derived a formula, which you have in your formula sheet, and that RMS value is actually equal to the equivalent DC value, and that is why we use RMS values all the time, most of the time. In some cases, you do need to use the Vmax, but story for another day and for those who are interested in doing electrical engineering. But let's get to the calculations. So we're done with 9.3. Now 9.4. Calculate the RMS current in the circuit. Okay, cool. So as you see, our Vmax is actually 100 volts. Okay, and then according to our calculations, or you're looking at your formula sheet, you are going to use that formula that says Vmax is actually equal to Imax times R. And why am I doing that? I'm later going to use RMS is actually equal to Imax over root 2. Ne? Just checking the formula. Okay, so my Vmax in this case, like I have established, is actually 100. And if I want Imax alone, I'm going to have to divide by R. And they told me that the resistor is actually 25 ohm. Let me just check. Yeah, we have a 25 ohm resistor. So 100 divided by 25, that will actually give me 4. So my maximum current is actually 4 amperes. And I have my 4 amperes, and I'm going to divide it by root 2. So now my IRMS is going to be equal to 4 divided by root 2. And that will be 2,83. Okay, and that is the most stable current to use. Okay, and that was 9.4. All right, what else? Okay, 9.5. Calculate the average power dissipated in the 25 ohm resistor. Okay, so what is the average power formula? So average power is equal to V RMS multiplied by I RMS. Okay, so now V RMS, we need to go work that one out, or not even. Remember that V is equal to IR. So you can pretty much say power is I squared RMS multiplied by R. And our I squared was that 2,83, or you could say 4 over root 2 squared. If you want to get an answer that is not watered down, you can do that. And then, so this squared multiplied by 25. So we get an average power of 200 watts. Okay, so now we're not done. 9.6 is somewhere here. Let me just look for it. Okay, 9.6, there we go. I'm gonna try sketching here. So it says the speed of rotation of the coil in the generator is now doubled. Okay, now if the speed is doubled, remember we had our current, sorry, not our current, but our voltage. Let me just sketch it here rather, I'm gonna complicate my life. Okay, so difficult drawing straight. So I have let me just see the previous graph. Okay, let's just copy this out. So basically it's like this. I have 0,025, 0,05, 0,075, and that's 0,1, and that is time in seconds. Okay, that is V. We know that is 100, and we know that is negative 100. Okay, so now in this question they say the speed of the rotation of the coil in the generator is not doubled. So if your speed is doubled, so what would happen is your voltage, okay, it also increases. Okay, by how much? Well, they said it's doubled, so it will also double in that case. And also your speed, it talks about time, so your rate, not only will you reach a higher voltage, but you will reach it in a shorter space of time. Okay, so in that case I would have to if I were to draw this, is like saying, again, going back to your sine graph, your amplitude has now doubled and your period has been halved. So instead of completing a wave in 360, you're going to complete it in 180. Okay, so yeah. So now, where you had 100 as your max, you're going to have 200 as your maximum. If you didn't know, I guess the numbers here were to guide, but also that could be to mislead you, so you must know your story. Okay, and instead of reaching that peak at 0,025, you're going to reach it in half that time, so 0,0125. Okay, so you start at the same point, but you reach your peak earlier, and then you have it there, and then halfway there you reach 200. Okay, so now our graph, because they gave us one wave, I'm just gonna, can actually draw two waves. Yo, it looks terrible. But yeah, this is basically okay. Yeah, let's should reach its peak somewhere here. No, yeah, something looked funny. Okay, so to do that, it reach its peak here, then come and turn around there, and then there, and then that one there. Okay, let's try again. So basically a new graph would look like this. Okay, I tried. But yeah, that's pretty much that. And we are done with question 9. Please tune in for question 10 with my husband. And that's it from me. Bye.
Welcome to MV Tutors. My name is Figa Manana, and I will be doing this paper with you, this question. We are doing the 2021 final examination written in November. And this is physical science, paper number 1. This is the last question now, question number 10. Now, if this is what you want to do, then you came to the right place. Stick around. By the end of this, you would have understood what you needed to do. So, question 10 says, the relationship between frequency and maximum kinetic energy of photoelectrons emitted from two cathodes, M and N, of different photoelectric cells is investigated. The graph below have been obtained from the results. Okay, so I see that's the frequency there. That's the kinetic energy over on the x-axis. Define the term threshold frequency. So when we're speaking about a threshold frequency, this first number here, okay, so it's the minimum energy required, okay, to emit a photo electron. Okay, it's the minimum, rather the minimum frequency, not energy, minimum frequency required. Okay, just think of this minimum frequency required to emit photoelectrons. Okay, all right, so that's basically it. Now it's in metals because these cathodes are made of metals, and so it's, yeah, works with metals. Now let's go to the next question. How does the maximum kinetic energy of photoelectrons emitted from the cathode N compare to the maximum kinetic energy of those emitted by cathode N? When light of frequency greater than this is the threshold frequency of M, so a light greater than that is shown on each of the cathodes. So for this one, you can just pretty much demonstrate it. Okay, we have both of them like that. Okay, so this one is N and this one is M, right? So now if they said the frequency is greater than the threshold, so I can just do a frequency right over here like that. So if I continue there, I'm definitely M, N, okay. And if I go back there, you can see that M, the energy is here, but for m, it's actually greater. So the energy for n is actually greater than that of m. So when they say choose greater than, smaller than, or equals to, okay, the energy will be greater than. So we will choose greater than. Okay, so this was 10.2. Let's check out 10.3. Calculate the value of the frequency of fx indicated on the graph. Okay, let's go check out fx. So as you can see, fx has the frequency which is fx, and its energy required is 23.01 times 10 to the power minus 19. Okay, we can solve this. Okay, let's go for it. It should be 10.3. So we know that the energy is given by the work function plus the kinetic energy. Okay, so this one is given by a constant h and fx. The work function is also a constant h, but the frequency now is not a new frequency, it's the threshold frequency, the minimum one. And then plus, well, ek. In this case, we're given it. Okay, now we can start filling in. This constant h is actually given by 6.63 times 10 to the power negative 34. Okay, so we have times fx. That's going to be equals to, same thing, 6.63 times 10 to the power negative 34 times, now our threshold frequency is 10.40 is given in that graph of m, because we're dealing with m. So we'll just put 10.40 times 10, what's going on there, 4.0 times 10 to the power 14. Okay, and then we're gonna have to add the ek, the kinetic energy, and we've been given it here. It's 23.01 times 10 to the power negative 19. Wow. Okay, so all that's left now is just to do some mathematical gymnastics of actually dividing both sides by 6.63 to get fx. Okay, so what I'm gonna do is get a calculator, and then I'll start putting these numbers in. Okay, so on top I'll have this entire sentence here, so it's 6.63 times 10 to the power negative 34. Okay, and then come down times 10.40 times 10 to the power 14. Come down again, and then we have a plus. Plus what? Plus 23. Plus 23.01 times 10 to the power of negative 19. Negative 19, like that. And then we come downstairs with dividing by that. 6.63 times 10 to the power negative 34, because that's the constant. Okay, that's our final answer is 4. Our fx then is 4.51. I'll do it in 2 decimals, times 10 to the power 15. And what's the unit of frequency? It is hertz. Okay, so there we go. We're done with 10.3. Okay, let's go see the next question then. Okay, what's happening here in 10.4? So the experiment is now repeated for cathode M using the light frequency fx. So it's still the same frequency light, but of higher intensity. Okay, so we've increased the intensity now. How will each of the following be affected? Choose from increase, decrease, or no effect. Okay, so 10.4.1, what happens to the y-intercept of the graph? Okay, we're speaking about the M cathode. The y-intercept won't change, no effect. Why? Because the threshold is still the same. Okay, so no effect there, no effect. And then 10.4.1, what happens to the number of photo electrons emitted per unit time? So the number of photoelectrons will basically increase. Why? Because the intensity is higher. They increase the intensity, therefore photoelectrons emitted will increase. Okay, so it increases the number of photoelectrons. Oh, this was 2. Why did I write 1? So this is 3 now. The maximum kinetic energy emitted the maximum kinetic energy of the emitted photoelectrons. Okay, so the photoelectrons themselves, kinetic, it has no change, so it's no effect. Okay, there's no effect in the kinetic energy of the emitted photoelectrons themselves. There's just no change in those. By increasing intensity of the frequency light, it doesn't change the photoelectrons themselves. It just increases them being emitted. That's all. Okay, I hope you understood, but in the event that you didn't, you can contact me. I would love to be your tutor. You can contact me via my website www.mvtutors.co.za, or alternatively you can WhatsApp me on 076-312-1107. Okay, and before you do contact me, please speak to your parent or your guardian, because remember, at the end of the day, they are the ones who are paying for the tutoring services, so they need to be involved from the beginning of the process. Other than that, thank you so much, and I appreciate you.